All right, good afternoon, everyone. How's everyone doing?
Very good.
Very good. How about this side of the room? Are you very well and you're very good? Is that how this works?
We are great.
They're great. All right, perfect. So thank you all so much for coming. I'm disappointed that you're not in open spaces, but I'm also happy that you're here. So it's a bit of a double-edged sword. Today I'd like to talk to you about Base64 is not encryption. More specifically, I want to talk about Kubernetes Secrets. My name is Seth. I work on the developer relations team at Google. I've been at Google just under 2 years now. Prior to that, I worked at HashiCorp and Chef Software. So I've been involved in kind of the DevOps community, Devopsdays. I was actually the organizer, one of the organizers of Devopsdays Pittsburgh, in Pittsburgh, Pennsylvania, where I live. If you have questions, comments, complaints, or concerns, my Twitter handle is there. That's also my email at google.com. Feel free to tweet at me. My direct messages are open if you have questions that you don't feel talking about publicly. And I'll be around the rest of today, and I also have another talk tomorrow morning. So with that, this is a pretty technical talk. So I'm going to be showing code. I'm going to be doing some live demos. But there's also some high-level concepts in here. So we'll be kind of bouncing back and forth between slides and terminal. But before we do that, I want to talk and set some ground level here. Like, what is a secret? What are we actually talking about when I say the word secret? Because everyone has a different definition. And for the purposes of this talk, we're going to say that a secret is any credential, it's any configuration, API key, SSH credential that is required for an application at either build time or runtime, or both. So that might be like a Twilio API key to talk to some SMS service. That might be an AWS access key pair or a GCP service account credential. But anything that an application or service needs to run at build time or runtime. You may have other things that you're thinking about with secrets, like passwords. They might fall in here, but we're more specifically talking about infrastructure level secrets. And then this brings up an obvious question, which is why don't we just use public tweets to store all of our secrets? Like, why even care? Why should we even care? Why do we go to the effort of protecting secrets? Well, there's three main reasons. The first is that they're an incredibly attractive target for an attacker or a hacker. Oftentimes, this is because they're easily leaked in public repositories. If we look at many of the major, newsworthy security breaches that have happened, it's been because someone left an S3 credential or an AWS credential in a public Git repository that then someone was able to access a bunch of data from S3, or it's because someone left a Kubernetes API token in a public GitHub repo and then someone was able to access the dashboard and gain access to internal information. And then when you couple that with the fact that these secrets frequently include overly broad permissions, because you work at a startup and you just give everyone root access, because that's easy. No one has time to worry about like IAM permissions and privilege of least privilege principles, because like you have VC funding and you got to hit the deadline and like who cares? Everyone has root. And then like you start to become a real company, and that might not have been a great idea. And this is why these are kind of the three reasons that we want to protect secrets. And the latter two are why they're really attractive for an attacker or a hacker. They're often not scoped well, and they're often easily leaked. Like right now, how many people have a production credential on their laptop? If I were to grab your laptop and run out of this room, what would I be able to do? That's a really scary thought, right? How about this? If I were to pickpocket you and take your phone, what would I be able to do, right? How many people have production credentials on their phone in an email somewhere, right? None of you, because that would be a terrible idea. Anyway, there's 4 ways in which we as a security industry protect secrets. The first is auditing, and this is actually more on the other end. This is more of a response mechanism. All too often I see organizations focus all their time and effort in protecting against an attacker, and then they don't invest time in what happens when an attacker gains access to our system. They don't focus on revocation and rotation. They focus on detection and protection, and then they forget this first piece, the auditing and logging, the ability to quickly rotate a credential, the ability to inspect our system to see when a secret is being accessed, how frequently it's being accessed, and then potentially to bring some machine learning in there. It's like, hey, this secret has never been accessed at 3 o'clock in the morning from Sudan. Like maybe that's not someone, like maybe we should fire an alert for that, or at least log it and raise it to someone to take a look at in the morning. The second way that we protect secrets is through encryption. We always want to rotate secrets, or we always want to encrypt secrets at rest, but we also want to encrypt them in transit, primarily with something like TLS. It does you no good if you have like the world's best encryption for your hard drives and your secrets, and then you transmit them over HTTP. It really doesn't do much good, because anyone listening on that network has access to those secrets then in plain text. Rotation is another key piece here. The longer a secret lives, the more likely it is to be breached, either through a brute force attack or just through the inner workings of your system. You have something like an insecure TLS endpoint, someone gains access, is able to listen on the network. So we want to encourage frequent rotation. And then isolation is also important and incredibly relevant for this talk, and something that people often forget about is that you want to separate where your secrets are stored from where they're being accessed. And there's two main reasons you do this. The first is that it forces an attacker to compromise multiple systems, right? If I can just go in, attack that one system, get access to all your secrets, that's too easy. The second reason is that it encourages best practices and kind of leads to encryption, rotation, and auditing by proxy. It almost forces them to happen. Now, this talk is primarily going to focus on encryption, particularly with respect to Kubernetes, but the idea is very general. So we're going to specifically be focusing on encrypting secrets at rest. We're not going to be talking too much about the TLS in transit side of things, so specifically focusing on encryption at rest. And there's multiple ways in which you can encrypt data at rest, kind of ranging from specificity all the way up to just like general file system level encryption. So at the very kind of like the least granular level, or the lowest level, we have like machine level encryption or file system encryption. This is something like Apple File Vault or Windows BitLocker, where you have a key that key encrypts your hard drive. That way, if I steal your hard drive and run out, as long as you've shut your laptop down properly, I have to brute force that data. It's not sitting at rest in plain text on the hard drive. However, if I'm able to brute force that key, all of the data on that hard drive is now mine in plain text. As we move further up the stack, we introduce some complexity, but get added benefits. So when we move to something like service level encryption or application layer encryption, every piece of data in our system is encrypted with its own key. That key is then written to the hard drive, and then that hard drive might also be encrypted with file system permissions or file system level encryption. So if I were to somehow brute force the file system encryption key, the data itself is encrypted with its own key. And this has a few key advantages. So application layer encryption, or app layer encryption, is today the highest form of encryption, or the most granular form of encryption we have with respect to data granularity, and it offers a few key advantages. First, it's applied at the earliest possible step. So your application or service does the encryption before the data leaves the system. And this protects the data as it moves throughout the system, which was my next point. Oftentimes, like if you have a plain text secret and you give that secret to another service, you can't verify the integrity between that transmission. With app layer encryption, your service encrypts the data before it ever leaves the outer security boundary. And this gives you very, very fine-grained control over, does this particular piece of data get encrypted, does it not, with what type of cipher suite does it get encrypted with, and when the data leaves your system, it's encrypted. So even if it leaves your system on an unencrypted wire, like a non-TLS connection, it's still encrypted before it leaves the system. So that was a lot of background. Now let's talk about Kubernetes. Who likes Kubernetes? Why? I'm just kidding. So Kubernetes, as indicated by my 4 very sad faces, doesn't necessarily have the best defaults with respect to the way that it handles secrets. Now, Kubernetes obviously didn't start as like a security project, right? It started as a container scheduler and orchestration framework, and they've been adding lots and lots of security features. But one area in which Kubernetes continues to be a little bit behind the secrets management space is with respect to secrets. Specifically, I'm talking about Kubernetes secrets. Kubernetes secrets, which are like where your service accounts are stored, your service account tokens are stored, when you run kubectl create secret, or when you access a secret inside of a Kubernetes manifest, those are insecure by default. And what do I mean by that? I mean that those secrets, when you run kubectl create secret, they're stored in plain text in etcd. They're Base64 encoded, but that is not encryption. That is just a storage transport mechanism. It's just a different way to represent the data, and that's primarily so that you can have binary data like certificates in there. Now, what is etcd? If you're not familiar with Kubernetes, you can think of etcd like the file system. It's where Kubernetes puts all of its data at rest. And etcd is a distributed database, has consensus algorithms and some other nice things that Kubernetes leverages. But in general, think of it as a file system. So you can read this as Kubernetes puts secrets in plain text on the file system, and anyone with access to the file system can just ls and cat those files and get access to the plain text secrets. That's probably not great, because you can put all these RBAC permissions in the world, but then the moment someone gets access to your Kubernetes VM, they can just literally like ls the file system and get access to your plain text secrets. Now, before I move on, it's important to note that if you're running on like a cloud provider Kubernetes, like GKE or EKS or AKS, your cloud provider might alter this behavior. They may not give you access to the VMs. They may not give you access to etcd. So this is primarily targeted at people who are running on-premise Kubernetes clusters, things that you've spun up with like Coop Admin or spun up yourself. Maybe you're running on VMware, or maybe you're using a cloud provider that doesn't alter this default behavior. Now, let's take a look at what this looks like in a series of graphics. So I have a credit card here. It's not the best way to represent a secret, but it'll do. And then we have the Kubernetes API server and etcd, and they're all on a master VM or a master node. By default, no configuration. If I were to run Coop Admin and spin up a cluster today, this is what this would look like. Someone would run kubectl create secret with our credit card secret. That CLI call would translate into an API call. The payload would hit the Kubernetes API server. The Kubernetes API server would then Base64 encode that data and put it in etcd. How many people like my joke? Y'all like my Base64 joke? Anyway, obviously, even to the not people who get my Base64 joke, it's very clear that this is in plain text. It just has a slightly different appearance. So if an attacker, which we will represent via this red raccoon in all future slides, somehow has access to etcd, either online access to etcd because you've left your ports publicly exposed, offline access to a backup of etcd because you didn't secure your blob storage bucket, online access to the master VM itself because you leaked your SSH credential, or offline access to a backup of the file system of this master VM. The attacker has access to all of that data in plain text and etcd. And I know what you're thinking. You're thinking, oh, no one would ever publicly expose their etcd server. Like, that's not a thing. Well, that is a thing. And also, I call this encryption. You heard it here first. Actually, you heard it at FOSDEM a couple months ago, but that was the first time it was ever said. This is my word. I claim it. You're free to use it, but encryption is whenever you confuse encoding and encryption. And this is actually what the Kubernetes defaults exhibit. And if you think like, well, this is no big deal, like no one would ever do this, you know, most people are using a cloud provider, that's not the case. And if you don't believe me, you can check out Shodan, which is kind of like a search engine for the internet, and you can find all of the publicly exposed etcd clusters out there. And I'm not telling you to do this, because this would be a very bad thing. And I work for a company with a very big legal team that tells me to tell you not to do this. But there's a URL. But don't do this. So just to prove to you how terrible this is, I've spun up a VM, and all I've done on this VM is I've run Coop Admin in it. If you're not familiar with Coop Admin, it's like the kind of built-in Kubernetes tool for spinning up a cluster. So let me switch to mirror mode quickly. I told you we're going to do some demos. Who's exciting? Just this guy here in the front. It's fine. All right. Big font. OK, so this is Kubernetes. This is a single node cluster because I'm cheap. But this is a single node cluster in which we're running Kubernetes. And what I'm going to do here is I'm going to create a Kubernetes secret. So I'm going to run kubectl create secret generic. We'll call it login. And we'll do from literal equals username equals Seth Vargo dash from literal equals password equals, what's our password? Password 123, right? Okay. Cool, I created a secret. That was super great. Kubernetes is awesome. But where did that secret go? Does anyone want to take a guess while I pull up my cheat sheet, because I don't remember the command that I wrote? I was supposed to do this in advance, but you know, it's a live demo, so this is how you know it's real. Cool. So what I'm going to do now is I'm going to run etcd get. etcd is just one of the many ways in which I can interact with the etcd API. I could have used curl, but that's a really long command to type. So I'm just going to run etcd get, registry, secrets, default, login. And I'll zoom out just a little bit. I know that it's not super easy to see here, but there is some binary data in here, but this is the entry that's actually stored in etcd. So password 123 is very clearly there in plain text, and Seth Vargo is also very clearly there in plain text. And this data is actually on this file system in multiple places. It's in the etcd database itself. It's in the etcd write-ahead log, which is also stored on disk. And it's also replicated to any other etcd servers that are in this cluster, which in this example is just one. But if I had multiple etcd clusters, this data would be replicated all in plain text. This is obviously not great, because like I said, if an attacker has access to this or a backup of this or anything else, we've really not had a great experience leaking all of our credentials. So what can we do about it? Well, let's talk about envelope encryption. So envelope encryption is this concept which is really important for the rest of the talk, but I'm going to kind of run through it very quickly. Envelope encryption requires 3 pieces of information. We need your data, we have a data encryption key, and we have a key encryption key. And the way envelope encryption works is going to be explained through a series of very carefully crafted animations. That was the first one. So what we do is we have our piece of data and we want to encrypt it. We generate a new data encryption key, which is the red key, and we encrypt that data with that red key. Then we use a centrally managed key, something from like a key management store, and we encrypt the data encryption key. So now we have encrypted data and an encrypted key. We basically concatenate those together, and we put them in our storage backend. etcd, file system, Twitter, whatever it might be. When we want to reverse this process, we do the exact opposite. We separate the data apart, and then we use our key encryption key to decrypt the data encryption key, and then we use our data encryption key to decrypt the data. And then we get back the plain text data. So you might be thinking to yourself, why? Why not just use the green key to encrypt the data directly? Well, that's not really scalable, because with envelope encryption, we generate a new data encryption key each time we generate a new data entry. So if you have PCI or HIPAA or FIPS or XYZ compliance, you know that rotating your keys regularly isn't like one of those checkboxes that you have to fill out on that report. So every time you write a new piece of data, you generate a new data encryption key. And then you have your centrally managed keys, which you rotate on a regular interval. So this is a very scalable way to do encryption. So to just kind of summarize, we generate unique data encryption keys for every data entry. We can crypto shred because we can revoke the parent key encryption key, the green key, at any point in time. And that also effectively revokes all of the data encryption keys because you can't decrypt them anymore. It allows for easy versioning and rotation. We can separate like what gets rotated when. Cool. So now let's talk about Kubernetes 1.7. So Kubernetes 1.7 introduced envelope encryption. So that algorithm that I just described is actually built into Kubernetes 1.7, but it's not the default. You have to go activate it yourself. This is how you do it. Because we're all YAML engineers, we have to write some YAML. This is an encryption configuration. This is a YAML configuration file that you load into Kubernetes. You actually specify the keys. So that is a key, that is a key, that is a key. You also specify the algorithm. You can use CBC or GCM keys, secret box. There's a bunch of different configurations here. So you have this configuration. You have to generate those keys yourself. You have to manage this file yourself. And you have to start the Kubernetes API server with this configuration. It's a special flag, --encryption-provider-config, which will read that configuration, and lo and behold, your sequence will be encrypted. It'll look just like this. You'll have your data will hit the Kubernetes API server. The Kubernetes API server will delegate to the encryption configuration, which will encrypt your data before it's sent to etcd. The problem is solved. Or is it? So if an attacker has access to etcd, like an online access to etcd, or they have access to a backup of etcd, we have solved the problem. The attacker does not have access to the plaintext data. But what if an attacker has access to the live VM or a backup of the VM? Well, I don't know if you noticed, but the keys were in plain text in that YAML file on disk. So all you've done is you've given an attacker a really good, like, Santa-style laugh. Ha, ha, ha. And they have moved on with their life. Because it's just an O of N operation to decrypt all of this data. So from a security perspective, we haven't actually improved dramatically. There's a few other drawbacks. We have to generate those keys ourselves. Who knows the OpenSSL command to generate a 32-bit key? I do because I wrote this talk. I didn't before I wrote this talk. Key management is your responsibility. Every time you create a new key, update a key, rotate a key, you have to restart the Kubernetes API server, which could cause downtime. couple seconds, couple minutes. If you mess up that configuration, the Kubernetes API server will refuse to start, which is probably the right behavior, but it's not great if you're in the middle of the day and your developers are trying to deploy. There's no HSM integration. HSMs are hardware security modules. If you work in like fintech or a regulated industry, you're likely familiar with these. They're literally physical devices. This doesn't work with those. So if you have regulatory requirements for HSMs, you can't use this. But as we already discussed, the largest drawback is that the underlying encryption keys are in plain text in the file system. And if we remember before, we talked about isolation being a key piece of the secrets management story. And this does not practice isolation. We have our keys stored in the same place that our data is accessed, and that's a bad practice. It's an anti-practice. So we worked really hard internally at Google and with a number of the SIGs in the Kubernetes community, and Kubernetes 1.10 introduced this concept of encryption provider configurations. And they look a little bit like this. So it's that same encryption provider configuration that we saw earlier, but instead of specifying the keys, we're specifying the endpoint, which in this example is a Unix socket, but it could also be like a HTTPS endpoint. And we're delegating encryption to a third-party KMS plugin or KMS provider plugin. So this looks very similar to what we've seen before. The data hits the Coop API server. The Coop API server delegates to the encryption configuration. The encryption configuration, though, delegates encryption to a third-party key management service. This is most likely a cloud provider managed service, something like Cloud KMS or Amazon KMS. That returns ciphertext, and that ciphertext is then stored in etcd. So now, if an attacker, and to reverse the process, it's exactly the opposite. We have to make that API call back to KMS. So if an attacker has access to the master VM, they don't actually have access to the plaintext data anymore. Now, there is a slight nuance here, which is that an attacker has online access to the data. So if you leak your SSH key, an attacker can connect to the master node and use the authentication of the master node to communicate with KMS to decrypt the values. But if they have an offline backup of your VM, they can't decrypt that data because your backup doesn't have permission to talk to KMS. And there's other ways that we can further mitigate that, but I don't have a lot of time to discuss them. Now, you might be thinking to yourself, this looks really hard. I don't want to build a plugin. Writing Go is hard. I don't understand Kubernetes. That's OK, because every major cloud provider actually has published one or has worked with like community partners to publish one. So for example, at Google Cloud, we have published one that integrates with our KMS provider. You can run this on Google Cloud Kubernetes Engine, or you can run it on your own managed Kubernetes. Azure has one as well. The Kubernetes SIGs have one for AWS, and Oracle actually has one for HashiCorp Vault, which we'll talk about in a second. So these plugins already exist. They're pretty easy to install and manage. You can install them and run them like on the host. You can run them in a container. You can run them via systemd. You can run them via Upstart if you're stuck in 2012. There's a number of ways that you can run them. Shameless plug, because it's something that I worked on. If you are on Google Cloud, we actually do this for you with like a simple flag and an API call. So you don't have to install a plugin. We'll do all of that for you. We'll manage the keys for you, or we'll give you the ability to manage the keys with just database encryption key when you create your cluster, and you can also do this in the UI. This is currently in beta. It's all built on the open framework and the open source tools that I mentioned. So you can install it yourself, or you can give this flag and we'll do it for you. One question I get asked a lot is like, how does the master VM know to talk to the KMS provider? Like, what does that authentication? We often call this the initial secret problem. And this is where a cloud provider's identity and access management can really help. So you can leverage identity and access management in your cloud provider to help solve that first secret problem by delegating that root of trust. And then privilege and access management also delegates to the identity and access management. And then we separate concerns as much as possible. So the nodes that are running etcd shouldn't have IAM permission to talk to KMS. And you should separate those as much as possible. That way an attacker, again, has to compromise multiple systems. And even if an attacker gains online access to a system that's able to decrypt data from KMS, you should have quotas and logging and alerting and auditing, such that if you see a mass collection of decryption requests hitting your KMS service all at once, that should be a flag. Someone should be paged. And you can proactively disable access to that key without revoking the key. And this is the advantage of having IAM in the middle there, is that you can take a soft cutoff while you do some investigation instead of revoking the key and then potentially incurring hours and hours of downtime or losing data. So let me show you what this looks like in the few minutes that I have left. How much time do I have left?
8.
I got 2 and 8, so we'll split the difference.
2 minutes for talk and 5 minutes for questions.
OK. Cool. So what I'm going to do is I'm going to go into this etcd manifest Coop API server. And what I'm going to do is I'm going to enable KMS encryption. And I suck at typing, so I have typed it out in advance. I'm going to save this file. And Kubernetes is so helpful that it watches the file system. So if I make a typo, it restarts the API server for me automatically and causes downtime. But if I don't make a typo because I typed out in advance, all I have to do is waste enough time. Kubectl get po -n kube system. We're wasting time. OK, we got some pending here. That's good. This guy is still restarting. Cool. So now we're back up and running. I'm going to delete the secret I created earlier. Kubectl delete secret. What do we call it? Login? Yeah. And then now that I've enabled this encryption provider config, I'm going to run the exact same command I ran earlier. So same username, same password, literally the same command. And it's going to come back really quickly. And then I'm going to run the same etcd command. And this will either work and I'll like mic drop, or it won't, and then it'll be awkward. Oh, it's because it's a login. And I get back a bunch of binary data. So the data is not in plain text. Thank you all so much. I have 5 minutes for questions.
Thank you so much, Seth.
Thank you. Oh, thank you.
So, are we taking questions? The mic box is over there. Do we have any questions for Seth?
You can ask me anything. What's up? There's a mic box.
Can we wait for the mic?
So we have we use environment variables as secrets, or we put them in secrets. How would you? And there's also connection strings in that file YAML. How would you suggest that we encrypt that kind of data? Because that's in Git and.
So you have what kind of secrets? Can you hold the mic a little bit closer? Sorry.
Oh, sorry. Well, there's sort of like we have alpha, beta prods use the same service, but just change the variables. But also there are like 3 connection strings that are secrets.
OK.
And right now we just have a secret file and create the secret for each namespace in the cluster. And even if we did all this encryption stuff, it would still be a YAML file somewhere that would sort of give us away. How should we go about that?
So if you have if there's ever a point at which you need to recover the plaintext data, you should store that in like an actual secrets management system. So that might be something like HashiCorp Vault. For more human things, that might be something like LastPass or 1Password. But then at some point, some operator or some system consumes those secrets in that connection string, encrypts them, whether that's with KMS or keys that you manage, and then puts them in a text file or into a Kubernetes secret encrypted. So within the runtime system, anything your users would access, you never want to have that in plain text. At Google, like many of our plain text secrets, like especially the most secure ones, are actually physically printed on a piece of paper and locked in a safe. Yeah. So like there's always a plain text backup somewhere in like a break glass scenario, but oftentimes they're very difficult to access, such as like physically printed on a piece of paper and in a safe, or they're stored in a third-party system that doesn't have access to production.
Okay. So sort of like create the secrets and then delete them, or
yeah,
store them. Okay.
And make sure that anytime someone accesses that secret, that there's some type of event that is generated, whether that's an email to the team that's like, hey, someone read the database secret from LastPass or 1Password or whatever, or just at least make sure that it's logged. That way you can correlate events.
Awesome. Thanks.
Other questions?
Great. Any other questions? No?
Can you show the Vault integration the remaining 2 minutes?
Yes. I can, but my
We have
computer went to
2
sleep.
minutes before Chris goes on stage, so
Provided I can type my...
no
I can't
pressure
even type
here.
my password. Okay. So yeah, bins. Where am I? PWD. I'm in the wrong folder. So bin create secret default. So this will create a default Kubernetes secret. I will access the secret in the default. You'll get back the plaintext. The Vault one is very similar. I will create the secret in Vault, and then I will access the secret for Vault, and you'll get back the encrypted data. How does this work? There's this fun setup script, which is a bunch of bash, but the key pieces are not in this file. The key pieces are in this file. So I'm going to zoom out here a little bit. So I install Vault. This is also open source. It's on Base64, it's not encryption on my GitHub. So I install Vault. I just run it in the file system locally because this is more of a local demo that I run in Minikube. I start Vault via systemd. I do some crazy auto unsealing, don't do what I do, and then transit is what you use. So you use the Vault Secrets enable transit. That will create a key. It's very similar to like a KMS key. And then I install the plugin. I have it on a bucket that I control just because I compiled it from source myself. And then you configure the plugin. It's pretty easy. It's YAML because it's Kubernetes. So you tell it the path, which is just transit, and then you tell it the key that you want to use, or keys, which is just my key in this example. This authentication is a little bit cheating because it runs locally, and then you run that as a service, so it runs under systemd. And yep, and then there's the Unix socket where it lives. The reason it lives in certs is because, again, this is like a hacky local demo, but the certs endpoint is automatically mounted in every pod that runs in the system, and I just didn't feel like dealing with adding more volume maps, so certs it goes. It's not production ready. Cool. Thank you all so much.
Thank you all. And thank you so much, Seth.
Thank you.